Have you ever wondered what it would feel like to witness the most violent event in the universe from the inside? Tonight, we're going inside a dying star, not just watching from afar, but following every moment as a stellar core the size of Earth suddenly realizes it can't support itself anymore. What happens when trillions of tons of matter fall inward faster than you can blink? We'll discover why electrons suddenly can't resist being crushed into protons. We'll feel the moment when matter becomes so dense that atoms themselves cease to exist. And then something remarkable happens. The core fights back, creating a shockwave so powerful it could obliterate planets. Using real data from gravitational wave detectors and neutron star observations, we'll experience temperatures that make the sun's core look freezing cold, and pressures that turn the laws of physics upside down. What does it sound like when space itself ripples? What does matter become when pushed beyond every limit? If curiosity about the universe's most extreme moments sparks something in you, your gentle like and subscribe would mean everything. Close your eyes. Let's step inside a collapsing star. Deep inside a star 20 times more massive than our sun, something extraordinary and terrifying is happening. For 10 million years, this stellar giant has burned through its nuclear fuel in perfect balance, fusing hydrogen into helium, then helium into carbon, carbon into oxygen, and onward through the periodic table. But tonight we follow its journey to the very end, where all fusion roads lead to iron. The core has become a sphere the size of Earth, yet it contains nearly 1.5 times the mass of our entire sun, compressed into that small space. At 3 billion degrees Kelvin with a density of 10 billion grams per cubic centimetre, this iron heart represents the star's final achievement and its ultimate doom. Unlike every element that came before, iron refuses to play by the rules of stellar fusion. When lighter elements fuse together, they release energy, feeding the star's furnace and creating the outward pressure that holds the star up against its own crushing gravity. But iron is different, special, cursed. Iron sits at the peak of the nuclear binding energy curve, making it the most stable nucleus in the universe. To fuse iron into anything heavier requires energy input rather than energy output. The star's 10 million year nuclear engine, the source of all its light and life, begins to stutter and die. Think about this moment for a breath. Every nuclear reaction that has kept this massive star shining, every photon that has pushed outward against gravity's relentless pull, every process that has maintained the delicate balance between collapse and explosion now faces its greatest enemy. The iron core grows larger with each passing hour as the surrounding shells continue their fusion dance, adding layer upon layer to this stellar graveyard. According to data from stellar evolution models, when this core approaches 1.4 solar masses, a limit calculated by Subrahmanyan Chandrasekhar in the 30s, the star reaches a point of no return. The electrons in the core, packed together at incredible densities, provide what physicists call electron degeneracy pressure. These electrons, governed by quantum mechanics and the Pauli exclusion principle, resist being compressed into the same space. For a while, this quantum pressure holds up against gravity's pull, but as the iron core grows heavier, approaching that critical Chandrasekhar mass, even the electrons begin to lose their battle. The core temperature climbs higher, the density increases, and the star's foundation starts to crumble. Picture this iron sphere, glowing white-hot at 3 billion degrees, sitting like a stellar cancer at the heart of what was once a magnificent star. The outer layers continue their nuclear burning, unaware that the very center of their existence is about to betray them. Shells of silicon fuse into more iron, neon burns into magnesium, oxygen creates silicon, carbon forms neon, helium produces carbon, and at the very surface, hydrogen still fuses peacefully into helium. The star looks normal from the outside, but inside it harbors a time bomb made of iron. When the core finally reaches that critical mass of 1.4 times our Sun, compressed into a space smaller than Earth, the electrons can no longer provide enough pressure to support it. The balance that has existed for millions of years, the perfect equilibrium between gravity pulling inward and pressure pushing outward, breaks forever. The star has built its own executioner atom by atom, reaction by reaction, over eons of nuclear fusion. It has unknowingly constructed the very instrument of its destruction. As we drift deeper into this stellar death story, imagine the irony. This star has spent its entire life fighting against gravity, winning for millions of years through the power of nuclear fusion. It has created and dispersed the elements that would one day form planets and life itself. Oxygen for the air we breathe, carbon for our bodies, silicon for the rocks beneath our feet, all forged in the nuclear furnace of stars like this one. But now, in creating iron, it has finally met its match. The core sits there, dense and hot and utterly unable to burn. The star's energy source has been cut off at its very foundation. Gravity, patient and relentless, begins to sense its opportunity. The outward pressure weakens as the nuclear fires dim. The iron core, this incredibly dense sphere of stellar ash, becomes increasingly unstable, and so begins the final chapter of this massive star's life. The next few moments will determine whether it becomes a neutron star, one of the densest objects in the universe, or collapses completely into a black hole. The stage is set for one of the most violent events the cosmos can produce. The star has taken its final breath. The great collapse is about to begin. Take a slow breath and imagine the most delicate balance in the universe. For 10 million years, this massive star has existed in perfect equilibrium, with every force precisely counteracting its opposite. At the heart of this cosmic dance lies a quantum mechanical phenomenon that most of us never think about. Yet it determines the fate of the most massive objects in our galaxy. Electron degeneracy pressure, a force that emerges from the very foundations of quantum physics, has been the star's last line of defense against gravitational collapse. These electrons, packed together at unimaginable densities in the iron core, follow the Pauli exclusion principle discovered in the 1920s. No two electrons can occupy the same quantum state, which means they resist being compressed into the same space with a pressure that depends only on density, not temperature. For months, this quantum pressure has been locked in an epic struggle with gravity, and until now, it has been winning. But tonight, as we witness the final moments of stellar equilibrium, that balance breaks forever. The iron core has grown to exactly 1.4 solar masses, a number calculated with stunning precision by the young astrophysicist Subrahmanyan Chandrasekhar nearly a century ago. At this critical mass, squeezed into a sphere roughly the size of our Earth, the core reaches a density of about 100 billion grams per cubic centimetre. To put this in perspective, a teaspoon of this material would weigh as much as Mount Everest. The electrons are packed so tightly that they begin to move at speeds approaching the speed of light, and when particles reach these relativistic velocities, the rules change. Einstein's special relativity tells us that as particles approach light speed, the pressure they can exert becomes less effective at resisting compression. The faster the electrons move, the less they can push back against gravity's relentless pull. This is the moment when quantum mechanics meets general relativity, when the microscopic world of particles encounters the macroscopic force of space-time curvature. According to observations from neutron star studies and gravitational wave detectors like LIGO, we know this transition happens suddenly and catastrophically. The core structure, this Earth-sized sphere containing more mass than our Sun, represents the most extreme state of matter outside a black hole. Every cubic centimetre contains roughly the same density as an atomic nucleus, yet this is a sphere 12,000 kilometres across. Imagine every atom in the Earth compressed until the electrons and protons are touching, then multiply that density by a factor of 10. This is the environment where normal matter simply cannot exist. The electrons have been squeezed so close together that they occupy every available quantum state up to tremendous energies. In quantum mechanical terms, they form what physicists call a degenerate gas, where the pressure comes not from thermal motion, but from the fundamental requirement that particles cannot occupy the same space. Yet even this incredible quantum pressure has its limits. As the core mass edges toward the Chandrasekhar limit, the gravitational force per unit area increases faster than the electron degeneracy pressure can respond. Gravity grows stronger with the square of the mass, but the quantum pressure can only increase linearly with density. There comes a precise moment when these two curves intersect, when gravity's mathematical advantage becomes overwhelming. Data from supercomputer simulations show us that this transition happens rapidly, within minutes or hours, rather than the thousands of years that previous burning phases lasted. The electrons simply cannot push back hard enough anymore. Their quantum mechanical resistance, which has held for so long, finally admits defeat. The star core exists now at a density approaching that of atomic nuclei themselves, yet it still has further to fall. Imagine the nucleus of an atom expanded to the size of Earth, and you begin to appreciate the incredible compression already achieved, but atomic nuclei are separated by vast empty spaces filled with electron clouds. What happens when even those spaces disappear? The core has reached the point of no return, the moment when no known force in physics can halt the collapse. The electrons, despite their quantum mechanical stubbornness, despite the Pauli exclusion principle, despite moving at nearly the speed of light, cannot generate enough pressure to support 1.4 solar masses compressed into an Earth-sized volume. Gravity has been patient, accumulating mass slowly as the star burned through its fuel, waiting for exactly this moment when quantum mechanics would finally surrender. The balance that has defined this star's entire existence now tips irreversibly toward collapse. As we follow this cosmic drama deeper, we witness physics being pushed to its absolute limits. This iron core represents matter in a state that cannot exist anywhere else in the universe except in the hearts of dying massive stars. The point of no return has been reached. Gravity is about to win in the most spectacular way possible. Gravity has waited 10 million years for this moment, and now it claims its prize with breathtaking swiftness. The iron core, having reached the critical Chandrasekhar mass of 1.4 times our Sun, begins its surrender to the most fundamental force in the universe. What starts as an almost imperceptible inward drift becomes something far more dramatic within minutes. The initial collapse velocity seems almost gentle, just a few kilometers per second, like a slow-motion dance of stellar death. But gravity is deceptive in its patience. According to Einstein's general relativity, gravity is not just a force pulling objects together, but the very curvature of space-time itself. The massive iron core has been bending space-time around it for millions of years, creating an increasingly steep gravitational well. Now that the quantum mechanical resistance has failed, matter begins to fall down this curved space-time like water spiraling toward a drain, and the mathematics of freefall take over with relentless precision. Within the first few minutes, the collapse accelerates dramatically. The core, which has maintained its Earth-sized dimensions for months, begins to shrink noticeably. 10,000 kilometers becomes 9,000, then 8,000. The inward velocity doubles, then doubles again. Gravity feeds on itself in a positive feedback loop that grows stronger with every passing second. As the core becomes more compact, its gravitational field intensifies, pulling the remaining matter inward even faster. The density rises from 100 billion grams per cubic centimeter to 1 trillion, then 10 trillion. We are witnessing the most rapid transformation of matter in the known universe. During these critical minutes, something remarkable happens in the layers above. The outer shells of the star, still burning their nuclear fuel in shells around the iron core, have no idea that their foundation is crumbling beneath them. Light travels at 300 million meters per second, but even at this cosmic speed limit, information about the core collapse cannot reach the surface fast enough. The star's outer layers continue their fusion processes exactly as they have for thousands of years. Hydrogen burns to helium in the outermost shell, helium fuses to carbon deeper down, and the silicon burning zone still feeds more iron into the doomed core. These outer regions exist in a state of blissful ignorance, maintaining their steady nuclear rhythms while catastrophe unfolds below. The speed of sound in stellar material, which determines how quickly pressure waves can travel, is only a few thousand kilometers per second. At this rate, it would take nearly an hour for any disturbance to propagate from the core to the surface, but the collapse will be over in seconds, not hours. This creates one of the most dramatic examples of causality in astrophysics. The star's outer 90% of its mass continues burning fuel and radiating energy into space, completely unaware that its very existence is about to end. From our perspective, watching this stellar giant in the last moments before collapse, it appears completely normal. Its surface still glows with the same light it has emitted for millions of years. The fusion shells continue their patient work of creating heavier elements. The stellar wind still blows material into interstellar space. Nothing visible from the outside hints at the catastrophe brewing within. This is the cosmic equivalent of a controlled demolition, where the foundation is removed, but the building has not yet realized it should fall. According to numerical simulations run on the world's most powerful supercomputers, the transition from stable core to runaway collapse happens faster than any other process in stellar evolution. The previous burning phases lasted hundreds of thousands or millions of years. Silicon burning, the final nuclear process before iron formation, lasted only days. But core collapse happens in less than a second once it truly begins. The core shrinks from Earth's size toward the size of a city while we take a single breath. Gravity has become the only force that matters now. The strong nuclear force which binds protons and neutrons in atomic nuclei is overwhelmed. The electromagnetic force which keeps electrons in their atomic orbits is irrelevant. Even the electron degeneracy pressure that held up the core for so long is now powerless against gravity's exponentially growing strength. The core is approaching the point where only the most extreme physics applies, where matter behaves in ways that have never been tested in any laboratory on Earth. As we drift deeper into this story of cosmic destruction and creation, we witness the universe demonstrating its most extreme capabilities. This is the last quiet moment before the star discovers what physicists mean when they talk about the fundamental forces of nature. The core collapse has begun, and there is no force in the known universe that can stop it now. The beginning of the end has arrived, and it arrives very, very quickly. As gravity claims absolute victory over the iron core, we witness the most violent implosion the universe can produce. The collapse that began gently now accelerates into something that defies our everyday understanding of motion and speed. Within the first fraction of a second, the core's inward velocity reaches 10,000 kilometers per second, then 20,000, then 50,000. According to data from three-dimensional supercomputer simulations, the collapse velocity peaks at nearly 70,000 kilometers per second, which is 23% the speed of light. Nothing in our human experience moves this fast. The fastest spacecraft we have ever built would take months to travel the distance this collapsing core covers in a single second. To understand the sheer violence of this implosion, consider that the core shrinks from Earth's size to roughly 50 kilometers across in less than 1 second. Imagine our entire planet compressed to the size of a large city in the time it takes to blink. The mathematics of this collapse follow Einstein's equations for curved spacetime, where matter falls not through space but along the geometry of spacetime itself. Every atom in the core experiences an acceleration that dwarfs anything we can imagine. If you could somehow ride along with this collapsing matter, you would feel forces millions of times stronger than anything ever recorded on Earth. The core material accelerates inward faster than a bullet, faster than a rocket escaping Earth's gravity, faster than anything except light itself. This is what happens when the fundamental forces of nature are pushed to their absolute limits. What makes this collapse so extraordinarily fast is the principle of conservation of energy working on a cosmic scale. As the core shrinks, its gravitational potential energy converts to kinetic energy with devastating efficiency. Every gram of matter falling toward the center gains speed as it plummets down the gravitational well created by the core's immense mass. The deeper it falls, the faster it moves, and the faster it moves, the more kinetic energy it possesses. This energy has to go somewhere, and it goes into making the collapse even more rapid and violent. According to NASA's theoretical models, this process releases more energy than our Sun will produce in its entire 10 billion year lifetime, and it does so in less than a second. The core exists now in a state that has never been achieved in any laboratory on Earth. Imagine taking every atom in our planet and squeezing them into a volume smaller than the state of Rhode Island. The density climbs past anything we can easily comprehend. A sugar cube of this material would weigh more than all the cars on Earth combined. Yet this incredible compression happens so quickly that there is no time for the matter to reach thermal equilibrium. The collapse occurs faster than sound can travel through the stellar material, faster than any pressure wave can propagate, faster than any force except gravity can respond. This creates what physicists call a dynamical collapse, where the usual rules of stellar structure simply do not apply. During a normal stellar burning phase, the star maintains hydrostatic equilibrium with every force balanced against every other force. But during core collapse, only gravity matters. The electromagnetic forces that bind atoms, the nuclear forces that hold protons and neutrons together, even the quantum mechanical forces that govern electron behavior, all become secondary to gravity's overwhelming pull. The collapsing core has entered a realm of physics where only general relativity can accurately describe what happens next. Free-fall time calculations based on Newtonian gravity would predict a collapse lasting several minutes, but the actual collapse happens much faster. because Einstein's curved spacetime creates an even steeper gravitational well than Newton imagined. The core falls faster than a classical object would fall, accelerated by the very fabric of space and time itself. As the core shrinks from thousands of kilometers to hundreds to tens of kilometers across, we witness matter entering a state that exists nowhere else in the universe except at the moment of stellar death. The density approaches that of atomic nuclei, meaning that the empty space that normally exists between atoms has been completely eliminated. Picture an atomic nucleus expanded to the size of a football stadium, and you begin to appreciate the incredible compression achieved in core collapse. Every cubic centimetre now contains as much matter as a mountain. This is the most violent transformation of matter possible outside of a black hole's event horizon. As we follow this cosmic catastrophe deeper into its most extreme moments, we observe the universe demonstrating capabilities that stretch our understanding of physics to its breaking point. The core collapse represents the ultimate expression of gravity's power, the moment when one of the four fundamental forces overwhelms all others and reshapes matter into forms that challenge our most sophisticated theories. The Great Collapse has become an unstoppable force of cosmic destruction. As the core continues its catastrophic collapse, we witness one of the most profound transformations in the universe, the complete destruction of atomic matter as we know it. The temperature has now climbed past 10 billion degrees Kelvin, and at these incredible energies, the very building blocks of matter begin to change. The electrons that once provided quantum mechanical pressure can no longer maintain their separate existence from protons. According to the laws of particle physics, when electrons and protons are forced together under extreme pressure and temperature, they undergo what scientists call electron capture, a process that fundamentally rewrites the composition of matter itself. In this cosmic furnace, electrons crash into protons with such violence that they merge to form neutrons and neutrinos. The equation is elegantly simple yet cosmically devastating. Electron plus proton becomes neutron plus neutrino. Every time this reaction occurs, which is now happening trillions upon trillions of times per second throughout the collapsing core, two crucial things happen. First, the electron that was helping to support the core against gravitational collapse simply vanishes, replaced by a neutron that cannot provide the same quantum mechanical resistance. Second, a neutrino is born, carrying away energy and information about this stellar catastrophe at nearly the speed of light. The scale of this transformation defies human comprehension. The core, which began with roughly equal numbers of protons and electrons maintaining electrical neutrality, now converts most of these particles into neutrons. Within seconds, we witness the creation of approximately 10 to the 58th power neutrinos, a number so large it strains our ability to visualize. If you could count one neutrino per second, it would take longer than the age of the universe multiplied by trillions to count them all. These neutrinos, nearly massless particles that barely interact with matter, stream out of the core carrying vast amounts of energy with them. Each electron capture event removes one more pillar of support from beneath the collapsing star. As the electrons disappear, transformed into neutrons and neutrinos, the quantum mechanical pressure that was the core's last defense against gravity crumbles completely. The core now consists almost entirely of neutrons packed together at unimaginable densities. According to data from neutron star observations and theoretical models of dense matter, these neutrons exist in a state unlike anything found elsewhere in nature. They are packed so tightly that they touch each other directly, with no empty space between them, creating what physicists call neutron degenerate matter. Imagine the nucleus of every atom in your body suddenly expanding until the neutrons touch, eliminating all the empty space that normally exists within atomic structure. This is the environment that now fills the entire collapsing core. The neutronization process represents the complete breakdown of the atomic world. Atoms, the fundamental building blocks of chemistry and biology, simply cannot exist at these densities and temperatures. The electromagnetic forces that hold electrons in orbit around nuclei become irrelevant when electrons are forced to merge with protons. The strong nuclear force, which normally acts only within atomic nuclei, now governs the behavior of matter throughout the core. We are witnessing the transformation from a world governed by atomic physics to one dominated by a nuclear physics. During this incredible metamorphosis, the core's composition changes from normal matter to what astronomers call neutron soup. Instead of atoms with their complex electron shells and chemical properties, we have a uniform sea of neutrons packed together at nuclear density. 1 teaspoon of this material would weigh approximately 6 billion tons, roughly the mass of Mount Everest compressed into the volume of a sugar cube. The neutrinos produced by this process carry with them the signature of stellar death. Unlike photons, which can take thousands of years to escape from the interior of a normal star, neutrinos barely interact with matter at all. They stream directly out of the core at nearly light speed, carrying news of the collapse to any detector sensitive enough to catch them. In 1987, astronomers detected exactly such a neutrino burst from supernova 1987A in the Large Magellanic Cloud, confirming our theoretical understanding of this process. 24 neutrinos were detected by experiments on Earth, particles that had travelled 60,000 light-years through space after being created in the death throes of a massive star. The moment atoms cease to exist marks a fundamental transition in the story of stellar collapse. Normal matter, with its familiar properties of chemistry and electromagnetism, gives way to exotic forms of matter that exist only in the most extreme environments the universe can create. The core has become a laboratory for testing the limits of physics, a place where the familiar rules of atomic behaviour surrender to the more fundamental laws governing neutrons and nuclear forces. As we continue deeper into this tale of cosmic transformation, we prepare to witness what happens when even neutrons reach their limit of compression. Tonight, we witness the birth of the most powerful particle beam in the known universe. As the stellar core undergoes its violent transformation from atomic matter to neutron soup, it unleashes what astronomers call the neutronization burst, a flood of neutrinos so intense it defies comprehension. This initial wave lasts only 10 milliseconds, a time span shorter than the blink of an eye. Yet in those fleeting moments, the dying star releases 10 to the 51st ergs of energy, purely in the form of neutrinos. To put this in perspective, this brief burst contains more energy than our Sun will produce in 100 million years of steady nuclear burning. The neutronization burst represents the universe's most efficient conversion of matter into pure energy, accomplished not through nuclear fusion or fission, but through the fundamental transformation of the building blocks of matter itself. During these crucial milliseconds, the core produces neutrinos at a rate that challenges our ability to visualize. Every second, approximately 10 to the 58th neutrinos stream outward from the collapsing core. If we could somehow count these particles as they emerge, we would need to count faster than all the computers on Earth combined, working together for billions of years. Each electron capture event, where an electron merges with a proton to form a neutron, creates exactly one neutrino. The core contains roughly 10 to the 57 protons, and as most of these undergo electron capture within seconds, we witness the most prolific creation of elementary particles ever observed in nature. These neutrinos possess energies between 10 and 30 million electron volts, making them far more energetic than anything produced in our most powerful particle accelerators. Unlike photons or any other form of radiation, neutrinos have an almost magical ability to escape from the stellar core. Normal matter is essentially transparent to neutrinos under most circumstances. A neutrino can travel through several light-years of solid lead without interacting with a single atom. This property, which makes neutrinos nearly impossible to detect under normal conditions, becomes their greatest strength during core collapse. While photons created in the core would take thousands of years to work their way out through the dense stellar material, neutrinos escape directly and immediately. They carry information about the core collapse at nearly the speed of light, racing ahead of any other signal that could emerge from the dying star. The collapsing core has become the universe's most powerful particle accelerator, not through electromagnetic fields or magnetic confinement, but through the sheer violence of gravitational collapse and nuclear transformation. The energies involved dwarf anything humanity has achieved in our most ambitious physics experiments. The Large Hadron Collider, our most powerful accelerator, can accelerate protons to energies measured in trillions of electron volts. But the dying star core produces neutrinos with energies in the tens of millions of electron volts, and it does so not for individual particles in a carefully controlled beam, but for every single one of the 10 to the 58th neutrinos it creates. The neutronization process transforms the core into a cosmic laboratory where nuclear physics operates under conditions impossible to reproduce on Earth. According to theoretical calculations based on the standard model of particle physics, each neutrino carries away not just energy but also lepton number, a quantum property that must be conserved in all particle interactions. As the electrons disappear through capture reactions, their lepton number is carried away by neutrinos, maintaining the fundamental balance required by the laws of physics. This process represents one of the most dramatic applications of conservation laws in the universe. The neutrino burst also marks the moment when the core becomes effectively transparent to its own radiation. In a normal star, photons created in nuclear reactions must undergo millions of scattering events as they slowly work their way outward through the dense stellar material. This process takes so long that photons created in the Sun's core today will not reach the surface for roughly 100,000 years. But neutrinos from the core collapse escape directly, carrying real-time information about the nuclear processes occurring in the stellar interior. They provide the only direct observational window into the heart of stellar death. During the brief neutronization burst, the core releases more power in neutrinos than all the stars in the observable universe produce in visible light. The neutrino luminosity peaks at values exceeding 10 to the 53 watts, a power output that strains our understanding of energy production mechanisms. This burst represents the opening salvo in what will become an even more sustained and powerful neutrino emission. The first wave is just the beginning of a neutrino storm that will continue for tens of seconds, carrying away nearly all the gravitational binding energy of the newly forming neutron star. As we drift deeper into this cosmic drama, we prepare to witness how these invisible messengers will ultimately determine whether the star explodes in a supernova or collapses completely into a black hole. The neutrino storm has begun, and with it, the universe demonstrates its most extreme methods of energy transport and particle creation. Now, as we follow the neutrino storm beyond its initial burst, we witness the most efficient energy transport mechanism the universe has ever devised. Over the next 10 to 20 seconds, the newly formed neutron star will radiate approximately 10 to the 53rd ergs of energy, almost entirely in the form of neutrinos. This represents 99% of all the energy released during the entire stellar collapse and explosion, making neutrinos not just messengers of stellar death, but the primary carriers of gravitational energy itself. To understand the magnitude of this energy release, consider that it exceeds the total energy output our Sun will produce during its entire 10 billion year lifetime by a factor of 100. Every second during the peak of neutrino emission, the collapsed core produces more energy than thousands of galaxies combined. Each individual neutrino carries between 10 and 30 million electron volts of energy, which may seem small on human scales, but becomes staggering when multiplied by the 10 to the 58th neutrinos being produced. According to observations of supernova 1987A and theoretical models based on neutron star cooling, these neutrinos emerge from the proto-neutron star in three distinct flavors: electron neutrinos, muon neutrinos, and tau neutrinos, along with their corresponding antineutrinos. The electron neutrinos carry slightly less energy on average, around 12 million electron volts each, while the heavier flavor neutrinos and antineutrinos each carry approximately 15 to 18 million electron volts. This energy distribution reflects the different ways these particles interact with the incredibly dense matter in the neutron star core. What makes this energy transport so remarkable is the speed at which it occurs. Unlike thermal conduction or convection, which move energy slowly through matter, neutrinos carry energy at essentially the speed of light. They stream outward from the neutron star core without delay, without scattering, without the countless interactions that would slow down photons or other particles. In effect, the collapsing star has discovered a way to instantly convert gravitational potential energy into radiation that can immediately escape to infinity. This process begins to reveal why stellar explosions are even possible. The gravitational binding energy of a neutron star, roughly 10 to the 53 ergs, represents an enormous reservoir of energy that was locked up in the star's structure for millions of years. When the core collapses from Earth size to city size, this binding energy is suddenly released and must go somewhere. If this energy remained trapped in the stellar interior, it would simply cause further heating and possibly further collapse. But neutrinos provide an escape route, carrying the energy away faster than any other mechanism could transport it. The neutrino emission effectively removes energy from the system, allowing the core to settle into its final neutron star configuration. During the first few seconds after core bounce, the proto-neutron star exists in a state of extreme thermal disequilibrium. The core temperature reaches 30 to 50 billion degrees Kelvin, far hotter than the surface. Thermal neutrinos pour out of this stellar furnace, carrying away both energy and heat, gradually cooling the interior. According to numerical simulations of neutron star formation, this cooling process follows well-understood physics of neutrino emission from hot, dense matter. The neutrinos interact weakly enough to escape freely, yet strongly enough to carry away the thermal energy efficiently. As the proto-neutron star cools and contracts to its final radius of approximately 10 to 12 kilometers, it continues to emit neutrinos for several minutes, though at steadily decreasing rates. The total energy budget of this process represents one of the most dramatic energy releases in astrophysics. The binding energy of the final neutron star, approximately 20% of its rest mass energy, emerges almost entirely as neutrinos. This mass-energy conversion follows Einstein's famous equation, but instead of converting mass to electromagnetic radiation as in nuclear fusion, stellar collapse converts gravitational binding energy directly to neutrino radiation. The efficiency of this energy transport mechanism makes possible what might otherwise seem impossible: a stellar explosion. Only about 1% of the released energy needs to be deposited in the stellar material above the core to unbind the entire star and create a supernova explosion. The remaining 99%, carried away by neutrinos, serves to remove the excess energy that might otherwise prevent explosion formation. According to data from gravitational wave observatories and neutrino detectors, this energy transport process operates with clockwork precision. The neutrino signal from stellar collapse carries information not just about the explosion mechanism, but about the fundamental physics of matter under extreme conditions. Each neutrino that reaches Earth from a distant supernova has travelled across cosmic distances, carrying within its energy and arrival time a record of the nuclear processes that occurred during stellar death. As we drift deeper into this story of cosmic energy transport, we begin to see how these invisible particles will ultimately determine the fate of the collapsing star, serving not just as messengers, but as active participants in the process of stellar destruction and creation. Take a slow breath and imagine an explosion so powerful it outshines entire galaxies, yet remains completely invisible to human eyes. At the peak of the neutrino emission, roughly 100 milliseconds after core bounce, the newly formed neutron star achieves a neutrino luminosity of 10 to the 55th ergs per second. This means that for a brief moment, this city-sized object produces more power in neutrinos alone than 10 million galaxies produce in visible light. The neutron star has become the brightest object in the universe, blazing with invisible fire that carries the signature of stellar death across cosmic distances. What makes this invisible explosion so remarkable is its composition. The proto-neutron star produces all 6 known types of neutrinos and antineutrinos: electron neutrinos, electron antineutrinos, muon neutrinos, muon antineutrinos, tau neutrinos, and tau antineutrinos. According to theoretical models of dense matter and weak nuclear interactions, each flavor carries slightly different energies and emerges from different regions within the neutron star core. The electron neutrinos, produced primarily through electron capture reactions, emerge with average energies around 12 million electron volts. The muon and tau neutrinos, created through thermal processes in the incredibly hot core, carry higher energies averaging 15 to 20 million electron volts. This diversity of neutrino types creates a complex energy spectrum that encodes information about the temperature, density, and composition of matter deep within the neutron star. The temporal evolution of this neutrino emission follows a precise pattern that astronomers have learned to recognize. The initial neutronization burst lasts only milliseconds and carries about 1% of the total neutrino energy. Then comes the main emission phase, lasting 10 to 20 seconds, during which the bulk of the energy emerges. The neutrino luminosity peaks within the first few hundred milliseconds, then declines exponentially as the proto-neutron star cools and contracts. According to simulations of neutron star formation, this cooling process follows the physics of neutrino emission from hot, dense nuclear matter, providing one of our few direct tests of nuclear physics under extreme conditions. On February 23, 1987, humanity received direct confirmation of this theoretical picture when supernova 1987A exploded in the Large Magellanic Cloud, a satellite galaxy 160,000 light-years from Earth. 3 neutrino detectors around the world, Kamiokande in Japan, IMB in Ohio, and Baksan in Russia, detected a total of 25 neutrinos arriving within a 13-second window. These particles had travelled across 160,000 light-years of space, passing through gas clouds, dust, and the magnetic fields of two galaxies. Yet they arrived carrying the precise energy signature predicted by the theories of core collapse. Each detected neutrino represented billions that passed undetected through the Earth, confirming that the vast majority of stellar collapse energy emerges in this invisible form. What made the 1987A detection so remarkable was the timing. The neutrinos arrived at Earth roughly 3 hours before the first light from the supernova became visible. This time delay reveals one of the most important aspects of stellar explosions. Neutrinos escape immediately from the core collapse, while light must work its way out through the dense stellar material above. The neutrino signal provides real-time information about the nuclear processes occurring in the stellar core, while the light we eventually see carries information about the shockwave's journey through the outer layers of the star. During those 3 hours between neutrino arrival and optical brightening, the explosion shockwave was still fighting its way outward through thousands of kilometers of stellar material. According to the physics of radiation transport, photons created by the explosion must undergo millions of scattering events as they diffuse through the dense stellar envelope. Each scattering event delays their emergence by a small amount, but the cumulative effect means that hours or even days pass before the first light escapes. Neutrinos, by contrast, stream directly out of the core without any significant delay, making them the earliest messengers of stellar death. The neutrino signal also reveals why some stellar collapses produce explosions while others form black holes directly. According to current theoretical understanding, successful explosions require that a small fraction of the neutrino energy, perhaps 1 or 2%, be deposited in the matter surrounding the neutron star core. If this energy deposition is efficient enough, it can revive the stalled shock wave and drive the explosion. If not, the continued accretion of matter onto the neutron star will eventually cause it to collapse into a black hole. The neutrino emission thus serves as both a consequence and a cause of stellar explosion. Future neutrino observatories with vastly improved sensitivity compared to the detectors that observed SN 1987A should be able to detect thousands of neutrinos from the next galactic supernova. This data will provide unprecedented insight into the physics of stellar death, allowing astronomers to study nuclear matter under conditions impossible to reproduce in any terrestrial laboratory. As we follow this cosmic drama toward its explosive conclusion, we prepare to witness how this invisible neutrino storm ultimately determines the fate of the dying star. Now we approach the most dramatic moment in the life of any massive star, the instant when collapse meets the ultimate wall that cannot be broken. The core, compressed beyond all earthly comprehension, reaches a density of 4 × 10⁻17 kilograms per cubic meter, a number that represents the fundamental limit of matter's compressibility. This is nuclear density, the same density found within atomic nuclei, but now spread across a sphere 10 to 15 kilometers in radius. To understand what this means, imagine taking every atomic nucleus in your body and expanding it until the neutrons and protons touch directly, eliminating all the empty space that normally exists within atoms. At this incredible density, a teaspoon of core material would weigh 6 billion tons, roughly the mass of Mount Everest compressed into the volume of a sugar cube. The core has reached a state of matter so exotic that it exists nowhere else in the universe except in the hearts of neutron stars and during these fleeting moments of stellar death. According to the laws of quantum chromodynamics, the theory that describes the strong nuclear force, neutrons themselves become a degenerate quantum fluid at these densities. Just as electrons provided quantum mechanical pressure earlier in the collapse through the Pauli's exclusion principle, neutrons now create their own version of degeneracy pressure. No two neutrons can occupy the same quantum state, forcing them to fill higher and higher energy levels as they are compressed together. This neutron degeneracy pressure represents the universe's final stand against gravitational collapse, the last quantum mechanical defense before matter surrenders completely to black hole formation. At nuclear density, something remarkable happens to the strong nuclear force itself. Throughout most of the universe, this force acts to bind protons and neutrons together within atomic nuclei, operating only over distances comparable to the size of nucleons themselves. But when neutrons are compressed to nuclear density, when they are literally touching each other in a cosmic game of subatomic billiards, the strong force reveals its repulsive character. According to quantum field theory, the same force that binds nucleons at normal nuclear distances becomes powerfully repulsive when they are squeezed beyond their natural separation. This creates what physicists call the nuclear equation of state, a relationship between pressure and density that governs the behavior of matter under the most extreme conditions imaginable. The core has become the hardest material in the universe, harder than diamond, harder than any substance that could exist under normal conditions. The neutrons resist further compression, with a pressure that increases dramatically with density. Theoretical calculations based on our understanding of quantum chromodynamics suggest that this nuclear matter is so incompressible that it approaches the rigidity of space-time itself. When the core reaches nuclear density, it essentially becomes a macroscopic atomic nucleus, a ball of neutrons roughly 10 kilometers across containing more mass than our Sun. The transition to nuclear density happens with stunning suddenness. During the collapse, the core density climbs steadily from billions to trillions of grams per cubic centimeter. But the approach to nuclear density represents a qualitative change in the nature of matter itself. According to numerical simulations of core collapse, the core spends very little time at densities just below nuclear density. Once the neutrons begin to touch, the equation of state stiffens dramatically, meaning that enormous pressures develop with only small additional increases in density. This stiffening creates the conditions necessary for core bounce, the moment when the inward collapse suddenly reverses direction. The physics governing this transition involves some of the most challenging theoretical problems in modern science. Nuclear matter at these densities may contain exotic particles like hyperons, strange quarks, or even more speculative forms of matter predicted by theories beyond the standard model. The exact composition of nuclear matter at several times nuclear density remains an active area of research with implications for our understanding of both stellar collapse and the fundamental nature of matter itself. What we do know is that the strong nuclear force operating through quantum chromodynamics creates an equation of state stiff enough to halt the collapse of stellar cores containing up to approximately 2 to 3 solar masses. Above this mass, even neutron degeneracy pressure and the repulsive strong force cannot prevent continued collapse to a black hole. The core has reached the point where only the most fundamental forces in nature determine what happens next. Electromagnetic forces, which govern chemistry and atomic physics, become irrelevant at these densities. Weak nuclear forces, responsible for radioactive decay and neutrino interactions, play only a secondary role. Gravity and the strong nuclear force now engage in the ultimate contest, with the fate of the star hanging in the balance. As we witness this cosmic collision between the irresistible force of gravity and the immovable object of nuclear matter, we prepare to see what happens when the universe tests the absolute limits of matter's resistance to compression. In one of the most violent reversals in the known universe, the core that has been collapsing inward at 70,000 kilometers per second suddenly becomes incompressible and rebounds like a cosmic rubber ball hitting an immovable wall. The moment nuclear density is reached, the neutron degeneracy pressure and repulsive strong nuclear force create an equation of state so stiff that further compression becomes nearly impossible. According to the laws of quantum chromodynamics, the core has encountered the fundamental limit of matter's compressibility. And when an irresistible force meets a truly immovable object, the result is one of the most energetic events the universe can produce. The bounce happens with stunning abruptness, occurring over milliseconds as the core's inward momentum is suddenly reversed by nuclear forces operating at the quantum level. All the kinetic energy of the collapsing core, accumulated during its violent inward fall, must be redirected somewhere, and that somewhere is outward in the form of a pressure wave of unprecedented power. This core bounce creates what physicists call a shock wave, a discontinuity in the stellar material where density, temperature, temperature and pressure change dramatically over distances much smaller than the shockwave itself. According to theoretical models and numerical simulations, the initial shock contains approximately 10 to the 51st ergs of energy, roughly equal to the energy our Sun will produce over 100 million years of steady nuclear burning. The shockwave represents the universe's most efficient mechanism for converting gravitational potential energy into kinetic energy, accomplished in a time span shorter than a human heartbeat. The formation of this shock occurs through a process that challenges our everyday understanding of how materials respond to compression. When the inner core reaches nuclear density and becomes incompressible, the outer regions of the core are still falling inward at tremendous velocities. This creates a traffic jam of cosmic proportions, wherein falling matter encounters matter that can no longer move inward. The result is a collision that generates temperatures exceeding 50 billion degrees Kelvin and pressures millions of times greater than anything found at the centre of the Earth. The shock wave begins its outward journey from the boundary between the incompressible inner core and the still-in-falling outer core, typically at a radius of 10 to 15 kilometers from the star's center. At the moment of formation, the shock front moves outward at speeds approaching 10,000 kilometers per second, roughly 3% the speed of light. This velocity represents the speed of sound in nuclear matter under extreme conditions, limited by the fundamental physics of how pressure waves propagate through dense stellar material. Behind the shock wave, the core settles into its new configuration as a proto-neutron star, an object unlike anything else in the universe. This newly born compact object contains between 1 and 2 solar masses compressed into a sphere roughly the size of Manhattan. The proto-neutron star exists in a state of violent thermal disequilibrium, with core temperatures reaching 30 to 50 billion degrees Kelvin, while the surface remains relatively cool. According to observations of neutron stars and theoretical models of dense matter, this temperature gradient drives the intense neutrino emission that we witnessed earlier, as the proto-neutron star begins its long cooling process toward its final equilibrium state. The core bounce represents one of the most precise examples of energy conservation operating under extreme conditions. The gravitational potential energy released during the core's collapse, accumulated over millions of years of stellar evolution, is suddenly converted into the kinetic energy of the shock wave in a matter of milliseconds. This energy conversion follows Einstein's general relativistic equations, modified by the nuclear equation of state to account for the behavior of matter at nuclear densities. The efficiency of this energy conversion is remarkable, with nearly all the available gravitational binding energy appearing in the shock wave's initial energy budget. During the bounce, the core also undergoes a fundamental change in its internal structure. The chaotic dynamical collapse phase gives way to a more ordered configuration governed by hydrostatic equilibrium, modified by the extreme conditions of nuclear matter. The proto-neutron star begins to establish the density and temperature gradients that will characterize its long-term evolution. According to studies of neutron star structure, the core likely develops distinct regions: an inner core of pure neutron matter, an outer core containing neutrons mixed with protons and electrons, and eventually a solid crust of increasingly exotic nuclei. The shockwave itself carries the imprint of the nuclear equation of state, encoding information about the fundamental properties of matter under conditions that cannot be reproduced in any terrestrial laboratory. The wave's strength, speed, and energy content all depend critically on how nuclear matter behaves at densities several times greater than that of atomic nuclei. As the shock begins its journey outward through the remaining stellar material, it carries with it the power to either explode the star in a brilliant supernova or stall and allow continued collapse into a black hole. The bounce has created a proto-neutron star and launched a shockwave, but the story of stellar death has only just begun. As the shockwave begins its heroic journey outward from the newly formed neutron star, it encounters obstacles that threaten to turn stellar death into stellar failure. Within the first few milliseconds after core bounce, the shockwave faces two devastating energy loss mechanisms that drain its power and slow its progress. First, as the shock plows through the iron-rich material surrounding the core, the extreme temperatures behind the shock front cause photodisintegration, the same process that weakened the core during its initial collapse. High-energy gamma rays created by the shock's passage have enough energy to tear apart iron nuclei, breaking them down into alpha particles and individual nucleons. According to nuclear physics calculations, this process absorbs approximately 9 million electron volts per iron nucleus destroyed, siphoning away enormous amounts of energy that the shock needs to continue its outward propagation. Second, the shock wave becomes a prolific producer of neutrinos through the same electron capture reactions that occurred during core collapse. As the shock compresses and heats the stellar material, electrons crash into protons to form neutrons and neutrinos, and these neutrinos immediately escape, carrying energy away from the explosion. The combination of nuclear dissociation and neutrino cooling creates an energy drain so severe that the shock begins to lose momentum within seconds of its formation. By the time the shock has traveled 100 to 200 kilometers from the neutron star core, roughly the distance from New York to Philadelphia, it has lost so much energy that its outward velocity drops dramatically. According to three-dimensional computer simulations performed on the world's most powerful supercomputers, the shockwave stalls at this radius, becoming what astrophysicists call a standing accretion shock. Instead of continuing its explosive journey to the stellar surface, the shock becomes stationary, neither moving outward nor inward, suspended in a precarious balance between energy input from below and energy lost to its surroundings. This creates one of the most challenging problems in modern astrophysics, known appropriately as the standing shock problem. The simple picture of core bounce leading directly to stellar explosion, which seemed so natural and inevitable, fails to explain how real supernovae actually occur. The shock stalls well short of the stellar surface, trapped in a region where energy losses exceed energy gains. If nothing intervenes to revive the shock, it will remain stationary, while matter continues to fall onto it from the outer layers of the star. This ongoing accretion presents the stalled shock with an additional challenge. The material falling through the shock from the outer regions of the star carries kinetic energy inward, but this energy is not sufficient to overcome the massive energy losses occurring behind the shock front. According to models of stellar structure, the infalling matter has been accelerated by gravity during its journey from the outer layers, gaining speed as it approaches the shock. When this material encounters the shock, it is suddenly decelerated and heated, but the energy released is quickly radiated away by neutrinos. The shock finds itself in a losing battle, gaining energy from accretion, while losing even more energy to photodisintegration and neutrino emission. During the critical first few hundred milliseconds after core bounce, the fate of the entire star hangs in the balance at this stalled shock front. If the shock remains stalled for too long, continued accretion will add mass to the proto-neutron star, potentially pushing it beyond the maximum mass that neutron degeneracy pressure can support. According to theoretical calculations of neutron star structure, this maximum mass lies somewhere between 2 and 3 times the mass of our Sun, depending on the exact properties of nuclear matter at extreme densities. If the proto-neutron star exceeds this limit, it will collapse directly into a black hole, taking with it any hope of a supernova explosion. The standing shock problem reveals why stellar explosions are far more complex and delicate than early theories predicted. The universe cannot simply rely on core bounce to create supernovae. Instead, some additional mechanism must intervene to revive the stalled shock and drive it outward to the stellar surface. This mechanism must operate on timescales of hundreds of milliseconds, faster than the proto-neutron star can accrete enough mass to collapse into a black hole, yet efficiently enough to overcome the tremendous energy losses that stalled the shock in the first place. The explosion that seemed inevitable after such a violent core bounce now appears to be the exception rather than the rule, requiring precise conditions and delicate timing to succeed. As we continue deeper into this cosmic drama, we prepare to discover how the universe solves the standing shock problem, transforming stellar death from a failed explosion into one of the most spectacular events in astrophysics. The stalled shock awaits revival, and the neutrinos that have been carrying energy away from the explosion may hold the key to its salvation. In the minutes following core bounce, as the shock wave sits stalled and seemingly defeated, the neutrinos that have been streaming away from the proto-neutron star begin to play an unexpected role as cosmic saviors. Deep in the theory of neutrino interactions with dense matter, physicists discovered that under the extreme conditions behind the stalled shock, a small fraction of the escaping neutrinos can deposit their energy in the stellar material, creating what astronomers call the neutrino heating mechanism. This process operates in a narrow region between the neutron star surface and the stalled shock front, typically extending from 30 kilometers to about 150 kilometers from the center. According to calculations based on the weak nuclear force, neutrinos interact with matter through reactions that can either heat the material by depositing energy or cool it by carrying energy away. The critical insight is that there exists a specific radius, called the gain radius, where neutrino heating exceeds neutrino cooling for the first time since core bounce. Below this radius, closer to the neutron star, neutrino interactions remove more energy than they deposit because the matter is so dense that neutrinos are produced more efficiently than they are absorbed. Above the gain radius, in the region behind the stalled shock, the density has dropped enough that incoming neutrinos from the neutron star can deposit more energy than the local matter radiates away. This creates a thin shell of neutrino-heated material that becomes the engine for shock revival. The physics of this heating mechanism depends on the fundamental properties of neutrino interactions as described by the standard model of particle physics. Electron neutrinos interact with neutrons through charged current reactions, converting neutrons to protons while depositing energy and momentum. All flavors of neutrinos and antineutrinos can scatter off nucleons through neutral current interactions, transferring energy without changing the particle identities. According to theoretical calculations, the total energy deposition rate in the gain region reaches approximately 10 to the 50 ergs per second during the critical phase of shock revival, representing about 1% of the total neutrino luminosity from the proto-neutron star. This seemingly small fraction becomes crucial because it represents the only energy source capable of referring the stalled shock against the ongoing energy losses from photodisintegration and neutrino cooling. The success or failure of the neutrino heating mechanism depends on a delicate race between competing timescales that determine the ultimate fate of the explosion. The heating timescale measures how long neutrino energy deposition takes to unbind the matter in the gain region from the gravitational attraction of the neutron star. According to numerical simulations, this process typically requires several hundred milliseconds of sustained neutrino heating. The competing advection timescale measures how quickly matter flows through the gain region, either falling onto the neutron star or being ejected by the shockwave. If the advection time is shorter than the heating time, matter passes through the gain region before neutrino heating can unbind it and the explosion fails. If heating wins this race, the neutrino energy can drive the shock revival and create a successful supernova explosion. This competition creates an incredibly sensitive dependence on the detailed structure of the progenitor star and the properties of the neutron star equation of state. According to data from three-dimensional supercomputer simulations, the critical parameter appears to be the ratio of heating time to advection time, with successful explosions requiring this ratio to be less than approximately 1. Stars with more compact cores have shorter advection times, making explosion more difficult. Proto-neutron stars with larger radii have higher neutrino luminosities, making heating more effective. The neutrino heating mechanism reveals why stellar explosions are so rare and require such precise conditions. Only about 1% of the enormous neutrino energy flux from the proto-neutron star contributes to shock heating, and this energy must overcome the substantial losses from nuclear dissociation and continued neutrino cooling. The process requires not just enormous energy production, but precisely controlled energy deposition over hundreds of milliseconds in a narrow shell of stellar material. During this critical phase, the proto-neutron star serves as both the energy source for revival and the gravitational anchor that threatens to pull material inward before heating can occur. As we drift deeper into this cosmic balance between explosion and collapse, we prepare to witness how turbulence and convection amplify the neutrino heating mechanism, transforming this delicate energy balance into the chaotic dynamics that ultimately determine whether the star lives or dies in the most spectacular explosion the universe can produce. Behind the stalled shockwave in the thin shell where neutrino heating has begun to deposit energy, the stellar material erupts into the most violent turbulence the universe has ever produced. What begins as a smooth, spherically symmetric flow quickly transforms into a seething cauldron of convective chaos that may hold the key to stellar explosion. According to three-dimensional magnetohydrodynamic simulations run on supercomputers, the neutrino-heated material becomes buoyant and begins to rise in hot plumes toward the shock front, while cooler, denser material sinks back toward the neutron star in a process that mirrors the convection in a boiling pot of water. At temperatures exceeding 10 billion degrees and densities millions of times greater than lead, this convective overturn operates on timescales of milliseconds, creating a dynamic three-dimensional structure that bears no resemblance to the orderly, layered stellar evolution that preceded core collapse. The hot neutrino-heated bubbles rise at speeds approaching 1,000 kilometers per second, carrying energy and entropy toward the stalled shock. When these bubbles reach the shock front, they deposit their energy and help push the shock outward. Meanwhile, the cool matter falling inward brings fresh material into the gain region, where it can be heated by the continuing neutrino flux from the proto-neutron star. This creates a convective cycle that amplifies the neutrino heating mechanism far beyond what spherically symmetric models predicted. The shock wave itself becomes unstable, developing what physicists call the standing accretion shock instability, or SASE, a phenomenon discovered only through detailed numerical modelling of the explosion mechanism. The shock front begins to oscillate and develop spherical distortions, sometimes moving inward in some regions while pushing outward in others. These oscillations occur with periods of several milliseconds and create spiral wave patterns that propagate around the shock surface. According to theoretical analysis of shock dynamics in curved spacetime, SASI arises from the feedback between the shock position and the flow of material through it, amplified by the acoustic waves that bounce between the shock front and the neutron star surface. The combination of neutrino-driven convection and SASI transforms the explosion from a spherically symmetric event into a fully three-dimensional phenomenon with complex asymmetries and turbulent mixing. These three-dimensional effects prove crucial for successful explosion because they dramatically increase the efficiency of energy transfer from neutrinos to the stellar material. In a spherically symmetric explosion, neutrino heating must overcome the energy losses uniformly across the entire gain region. But in the turbulent, asymmetric reality revealed by modern simulations, hot bubbles can break through the shock in localized regions, while other areas remain stalled, creating a pathway for the explosion to develop even when the average conditions would not support shock revival. The chaotic convection also creates the seeds for one of the most important observational signatures of neutron stars, pulsar kicks. The asymmetric explosion imparts momentum to the newly formed neutron star, giving it a velocity that can exceed 1,000 kilometers per second. According to observations of pulsar proper motions throughout our galaxy, these natal kicks are responsible for the high space velocities observed in many neutron stars, allowing them to escape from their birth clusters and populate the galactic halo. The magnitude and direction of these kicks depend sensitively on the detailed asymmetries developed during the explosion phase, making them a direct probe of the three-dimensional dynamics occurring during shock revival. During the critical few hundred milliseconds when the explosion hangs in the balance, this convective chaos serves as a cosmic amplifier, taking the modest energy input from neutrino heating and transforming it through turbulent mixing into a mechanism capable of unbinding the entire star. The smooth, orderly stellar evolution that lasted millions of years gives way to violent, chaotic dynamics that determine the fate of the explosion in a fraction of a second. According to the latest simulations incorporating magnetic fields, rotation, and detailed neutrino transport, successful explosions appear to require this three-dimensional turbulence to operate efficiently. One-dimensional models, no matter how sophisticated, cannot capture the essential physics of shock revival because they miss the crucial role of convective energy transport and turbulent mixing. As we continue deeper into this story of cosmic chaos and creation, we prepare to witness how this turbulent dance between hot and cool, rising and falling, ultimately breaks the stalemate between explosion and collapse, transforming stellar death into one of the most energetic events the universe can produce. In the cosmic drama unfolding behind the stalled shockwave, turbulent convection and neutrino heating finally begin to tip the balance toward explosion in a process that unfolds over hundreds of milliseconds, each one critical to the star's ultimate fate. The moment of shock revival arrives when the chaotic dance of hot rising bubbles and cool sinking material creates enough asymmetric pressure to break the deadlock between gravitational collapse and explosive expansion. According to three-dimensional simulations that follow the detailed physics of neutrino interactions and turbulent fluid flow, revival typically occurs between 100 and 500 milliseconds after core bounce, marking the transition from stellar death to stellar rebirth. The critical threshold for explosion requires the shocked material to gain approximately 10 to the 51st ergs of energy, roughly equivalent to the binding energy needed to completely unbind the outer layers of the star from the gravitational attraction of the central neutron star. This energy must be delivered through the delicate mechanism of neutrino heating operating in the narrow gain region, amplified by the turbulent mixing that increases the efficiency of energy's deposition by factors of 2 to 3 compared to spherically symmetric models. When heating finally wins the race against cooling and advection, the shock front begins to accelerate outward with renewed vigor, fed by the continuous energy input from neutrino interactions and the explosive burning of silicon and oxygen in the shock-heated material. The moment of revival determines one of the most important parameters of the explosion: the mass cut, the boundary between material that gets ejected into space and material that falls back onto the neutron star. According to stellar evolution models and nucleosynthesis calculations, This mass cut typically lies at around 1.5 to 2.5 solar masses from the stellar center, meaning that the innermost regions of the star, containing roughly 1.5 solar masses, collapse onto the neutron star, while everything above this boundary gets launched into interstellar space. The location of the mass cut depends critically on the strength and timing of shock revival, with earlier revival leading to lower mass cuts and more massive ejecta. The determination of what gets ejected versus what falls back creates the chemical signature that astronomers observe in supernova remnants and in the heavy elements distributed throughout galaxies. According to detailed nucleosynthesis calculations, the material just above the mass cut undergoes explosive silicon burning, creating iron peak elements like nickel-56, cobalt-56, and iron-56 that power the optical-like curves of supernovae through their radioactive decay. Further out, explosive oxygen burning creates elements like silicon, sulfur, and argon, while explosive carbon burning produces neon, sodium, and magnesium. The mass cut thus serves as the boundary between the exotic nuclear matter that becomes part of the neutron star and the heavy elements that enrich the interstellar medium with the products of stellar nucleosynthesis. During the critical revival phase, the neutrino luminosity from the proto-neutron star remains at approximately 10 to the 52 ergs per second, providing a steady energy source for continued heating as long as the shock can maintain its position in the gain region. The revival process creates a positive feedback loop where successful heating leads to shock expansion, which increases the volume of the gain region and allows more neutrino energy deposition. According to magnetohydrodynamic simulations that include the effects of stellar rotation and magnetic fields, this feedback can lead to exponential growth in the shock energy over timescales of tens of milliseconds once revival begins. The transition from stalled shock to successful explosion represents one of the most sensitive phase transitions in astrophysics, where small changes in initial conditions can determine whether a massive star becomes a neutron star with a modest supernova explosion, or collapses directly to a black hole with no visible explosion at all. The revival conditions depend on the detailed structure of the progenitor star, the properties of the neutron star equation of state, and the efficiency of neutrino heating in the gain region. Stars with more extended cores require more energy for successful explosion, while compact cores with steep density gradients can explode more easily. As the shock revival transforms stellar collapse into stellar explosion, we witness the universe converting gravitational potential energy into kinetic energy of the ejector, thermal energy of the shock-heated material, and nuclear binding energy of the heavy element that is forged in the explosion. The moment death becomes rebirth marks not just the end of one star's life, but the beginning of a process that will enrich the galaxy with heavy elements and trigger the formation of new generations of stars and planets. Once neutrino heating has broken the deadlock and shock revival begins, the stellar explosion transforms from a precarious balance into an unstoppable force of cosmic destruction. The shock wave, no longer stalled at a radius of 100 kilometers, begins to accelerate outward with exponentially increasing power as it encounters the decreasing density of the stellar envelope. According to hydrodynamic simulations that follow the shock's journey through the complex onion shell structure of the massive star, the acceleration occurs because the shock encounters progressively less resistance as it moves away from the dense core region. In the silicon-burning shell, the shock travels at speeds around 3,000 km per second, but as it breaks into the oxygen-burning region, its velocity increases to 5,000 km per second, then 8,000, then 12,000 as it climbs through the stellar atmosphere toward the surface. This acceleration creates a velocity profile where material ejected from deeper layers moves faster than material from the surface, leading to complex mixing and turbulence that will characterize the supernova remnant for thousands of years to come. Behind the accelerating shock front, the stellar material undergoes the most violent nucleosynthesis episode in the universe, a process called explosive burning that operates under conditions far more extreme than anything achieved during the star's normal lifetime. According to nuclear astrophysics calculations, the shock heats material to temperatures exceeding 5 billion degrees Kelvin in a matter of seconds, creating an environment where nuclear reaction rates increase by factors of millions compared to hydrostatic burning. In the shocked silicon and oxygen-rich layers, explosive silicon burning converts these elements into iron peak nuclei in minutes, rather than the days required during the normal stellar evolution. The shock provides both the temperature needed for rapid nuclear reactions and the neutron flux required to drive nucleosynthesis beyond iron through rapid neutron capture processes. Elements heavier than iron, which cannot be produced by the normal stellar fusion because they absorb rather than release energy, are forged in abundance during these explosive moments. According to detailed nucleosynthesis models, the shock-heated material undergoes rapid neutron capture, or R process nucleosynthesis, creating elements like gold, platinum, europium, and uranium that cannot be synthesized in any other astrophysical environment. The neutron flux in the shocked material reaches densities of 10 to the 24 neutrons per cubic centimeter, allowing atomic nuclei to capture neutrons faster than they can undergo radioactive decay. This creates highly neutron-rich isotopes that subsequently decay into stable heavy elements, producing roughly half of all elements heavier than iron found in the universe today. The shockwave also triggers what astronomers call explosive carbon burning and explosive oxygen burning in the appropriate stellar layers, processes that create intermediate mass elements like neon, magnesium, silicon, sulfur, argon, and calcium. As the shock propagates through each compositional shell of the evolved star, it encounters material with different nuclear properties and creates different nucleosynthesis products. The shocked helium layers produce carbon, nitrogen, and oxygen through explosive helium burning, while the hydrogen envelope experiences explosive hydrogen burning that creates trace amounts of lithium, beryllium, and boron. During this explosive nucleosynthesis phase, the star begins to tear itself apart from the inside out as the shockwave converts the carefully layered onion shell structure built up over millions of years of stellar evolution into a chaotic, turbulent mixture of hot gas expanding at thousands of kilometers per second. According to computational fluid dynamics simulations, Rayleigh-Taylor instabilities develop at the interfaces between different composition layers, creating mushroom-shaped plumes of heavy elements that rise through lighter material. These mixing processes ensure that the nucleosynthesis products created in different layers become thoroughly mixed in the final supernova ejecta. The energy driving this explosive disruption comes from multiple sources working in concert. The continued neutrino heating from the protoneutron star, the nuclear energy released by explosive burning reactions, and the kinetic energy deposited by the shockwave itself. According to energy budget calculations, the total explosion energy reaches approximately 10 to the 51st ergs by the time the shock breaks through the stellar surface, with roughly 10% coming from nuclear burning and 90% from the conversion of gravitational potential energy through the core collapse and bounce mechanism. As the shock accelerates toward the stellar surface, carrying with it the freshly synthesized heavy elements that will enrich the interstellar medium, we prepare to witness the moment when this cosmic catastrophe finally announces itself to the universe through the spectacular light display that we call a supernova explosion. Hours after the core collapsed and the shockwave began its violent journey outward, the explosion finally announces its presence to the cosmos in one of the most spectacular light displays the universe can produce. Shock breakout occurs when the accelerating pressure wave, having travelled through thousands of kilometers of stellar material at ever-increasing speeds, finally reaches the stellar surface and bursts into the vacuum of space. According to radiation hydrodynamics calculations, this moment represents a fundamental transition from the hidden violence occurring deep within the star to the brilliant optical display that astronomers observe as a supernova explosion. The shock breakout itself happens with stunning rapidity, occurring over minutes as the shockwave encounters the exponentially decreasing density of the stellar atmosphere and accelerates to velocities approaching 30,000 kilometers per second. When the shock finally breaks through the photosphere, the visible surface of the star, it creates a burst of high-energy radiation that briefly outshines the entire star by factors of thousands. The first photons to escape carry the signature of shock breakout, a flash of ultraviolet and X-ray radiation that lasts for hours and provides astronomers with direct information about the explosion energy and the structure of the stellar surface. According to observational data from space-based telescopes, this breakout flash has been detected in several nearby supernovae, confirming theoretical predictions about the shock propagation mechanism and providing crucial tests of explosion models. Following the initial breakout flash, the expanding shockwave creates a fireball of hot gas that begins to cool and emit the characteristic light curve of a Type II supernova explosion. The total explosion energy reaches approximately 10 to the 44th joules, which represents roughly 100 times the total energy our Sun will produce during its entire 10 billion year main sequence lifetime. This enormous energy release drives the ejection of 10 to 20 solar masses of stellar material into interstellar space at velocities ranging from 1,000 to 10,000 kilometers per second. According to spectroscopic observations of supernova ejecta, the fastest moving material comes from the innermost regions near the mass cut, while the outermost hydrogen envelope expands more slowly, creating the complex velocity structure observed in supernova remnants. The light we observe from supernovae comes primarily from the radioactive decay of nickel-56 and its daughter products, created during the explosive nucleosynthesis phase. Approximately 0.1 solar masses of nickel-56 are typically produced in core collapse supernovae, and the energy released by its decay to cobalt-56 and then to iron-56 powers the supernova light curve for months after the explosion. According to nuclear physics calculations, each nickel-56 nucleus releases about 3.7 million electron volts during its decay chain, and the cumulative effect of 10 to the 57 nuclei undergoing this process creates a luminosity that can exceed 10 billion times the brightness of our Sun at peak. The expanding ejecta create a supernova remnant that will continue to evolve for thousands of years, gradually slowing as it encounters the resistance of the interstellar medium, but continuing to expand until it has swept up many times its own mass in surrounding gas. The explosion enriches the galaxy with heavy elements forged during stellar evolution and explosive nucleosynthesis, dispersing oxygen for future atmospheres, silicon for rocky planets, iron for planetary cores, and gold for jewelry across hundreds of cubic light-years of space. According to galactic chemical evolution models, supernova, like this one, are responsible for creating and distributing most elements heavier than helium found in the universe today. The birth of this supernova marks not just the death of one massive star, but a cosmic recycling of air that makes possible the formation of planets and life in future generations of stellar systems. The shockwave will continue expanding for millennia, triggering the formation of new stars as it compresses nearby gas clouds while simultaneously enriching them with the heavy elements necessary for planet formation. The explosion energy of 10 to the 44th joules will gradually dissipate into the kinetic energy of expanding gas, the thermal energy of heated interstellar medium, and the gravitational potential energy of gas lifted from the galactic plane. For the next several months, this newborn supernova will blaze across the cosmos with a luminosity that can be detected by telescopes billions of light-years away, making it temporarily visible to observers in distant galaxies as a single point of light that rivals the combined brightness of 100 billion stars. According to photometric observations of Type II supernovae, the light curve reaches maximum brightness approximately 90 days after explosion, when the expanding ejecta have become transparent enough for the radioactive glow from deep within to shine through. The supernova remains visible to optical telescopes for 6 to 12 months, gradually fading as the radioactive nickel-56 and cobalt-56 created during an explosive nucleosynthesis undergo decay with half-lives of 6 and 77 days respectively. Each decay event releases gamma rays that are absorbed by the surrounding ejecta and re-radiated as visible light, creating a cosmic lighthouse powered by nuclear physics that advertises the death of a massive star across intergalactic distances. During this extended light show, the expanding supernova remnant begins the most important phase of its cosmic mission, the dispersal of heavy elements throughout the local region of the galaxy. According to stellar nucleosynthesis calculations, this single explosion distributes approximately 5 to 10 solar masses of oxygen, 1 solar mass of silicon, half a solar mass of iron, and smaller but crucial amounts of calcium, sulfur, argon, and dozens of other elements into an expanding shell of hot gas. The explosion also creates and disperses approximately 0.1 solar masses of elements heavier than iron through our process nucleosynthesis, including gold, platinum, europium, and other rare elements that cannot be produced by any other known astrophysical process. This heavy element enrichment represents one of the most important functions of massive stars in galactic evolution, transforming hydrogen and helium from the Big Bang into the complex chemical inventory required for rocky planet formation and biological processes. The shockwave continues its expansion at velocities of several thousand kilometers per second, sweeping up and heating the surrounding interstellar medium in a process that will continue for tens of thousands of years. According to observations of galactic supernova remnants like Cassiopeia A and the Crab Nebula, These expanding shock waves create some of the most beautiful and scientifically important structures in astronomy, glowing shells of gas that reveal the internal structure of the explosion and provide laboratories for studying physics under extreme conditions. The shock-heated gas reaches temperatures of millions of degrees and glows brightly in X-rays, while the cooler outer regions emit visible light through the recombination of hydrogen and heavier elements. At the center of this expanding maelstrom sits the neutron star, the ultra-dense remnant of the original stellar core, now compressed to a radius of approximately 12 kilometers but containing more mass than our Sun. According to pulsar observations, this neutron star will likely spin rapidly, perhaps hundreds of times per second, due to the conservation of angular momentum during core collapse. If its magnetic field is properly aligned, it will emit beams of radiation that sweep across space like a cosmic lighthouse, creating the regular pulses that astronomers detect as a pulsar signal. The neutron star represents the most exotic form of stable matter in the known universe, with densities exceeding that of atomic nuclei and magnetic fields trillions of times stronger than Earth's. The entire supernova explosion and its aftermath represent a crucial component in the cosmic recycling program that makes complex chemistry and life possible throughout the universe. According to galactic chemical evolution models, the oxygen in Earth's atmosphere, the silicon in its rocks, the iron in its core, and the gold in our jewelry were all forged in the nuclear furnaces and explosive deaths of massive stars like this one. The calcium in our bones, the sulfur in our proteins, and the trace elements essential for biological processes were scattered into space by the supernova explosions that occurred billions of years ago in the regions where our solar system would eventually form. Without the cosmic recycling provided by stellar death and supernova explosions, the universe would remain a sterile collection of hydrogen and helium, incapable of forming the complex molecules that serve as the basis for planets, chemistry, and life itself. At the heart of the supernova remnant, where the most violent explosion in the universe has finally subsided, sits an object so extreme that it challenges our understanding of matter itself. The neutron star, born from the collapsed core of the massive star, now measures approximately 10 to 12 kilometers in radius while containing between 1.4 and 2.5 times the mass of our Sun compressed into this incredibly small volume. To appreciate the extraordinary nature of this cosmic object, consider that a neutron star is roughly the size of Manhattan, yet contains more matter than the star that lights and warms our entire planet. According to calculations based on the equation of state for nuclear matter, the density of a typical neutron star reaches 500 million tons per cubic centimeter, meaning that a sugar cube-sized piece of neutron star material would weigh approximately 1 trillion pounds, roughly equivalent to the mass of Mount Everest compressed into a volume smaller than a dice. This represents the densest stable form of matter known to exist in the universe, approaching but not quite reaching the ultimate density limit where even neutrons would collapse into a black hole. The composition of a neutron star reflects the extreme nuclear physics operating at these incredible densities. According to theoretical models of dense matter validated by observations of neutron star masses and radii, approximately 95% of the star consists of neutrons packed together at nuclear density, while the remaining 5% includes protons, electrons, and possibly more exotic particles like hyperons or strange quarks in the deepest core regions. The neutrons exist in a superfluid state below temperatures of about 100 million degrees Kelvin, flowing without viscosity in quantum mechanical currents that can persist for millions of years. At the same time, the protons form a superconducting fluid that expels magnetic fields from the interior, creating the conditions for some of the most extreme magnetic phenomena in the universe. The magnetic field strength of a typical neutron star reaches values between 100 billion and 1 trillion times stronger than Earth's magnetic field, with some neutron stars called magnetars possessing fields up to 1,000 trillion times terrestrial values. According to magnetohydrodynamic theory and observations of pulsar emission, these enormous magnetic fields are generated and maintained by convective motions in the neutron star core during its formation and early cooling phases. The field lines threading through the neutron star surface create active regions where charged particles are accelerated to tremendous energies, producing beams of electromagnetic radiation that sweep across space as the neutron star rotates. Conservation of angular momentum during core collapse transforms what was once a slowly rotating stellar core into one of the fastest spinning objects in the known universe. According to pulsar timing observations, newly formed neutron stars can rotate hundreds of times per second, with the fastest observed pulsar spinning 716 times per second, completing a full rotation in just 1.4 milliseconds. As the neutron star ages and loses rotational energy through magnetic braking and gravitational wave emission, its spin rate gradually decreases over millions of years, but even old neutron stars continue spinning much faster than any other macroscopic objects. The surface of a neutron star presents conditions unlike anywhere else in the cosmos, with gravitational acceleration approximately 100 billion times stronger than Earth's gravity and escape velocities approaching 100,000 kilometers per second, roughly one-third the speed of light. According to general relativistic calculations of neutron star structure, the intense gravitational field creates significant curvature of space-time around the star, causing light to bend and time to dilate measurably compared to conditions in flat space-time. These extreme gravitational effects make neutron stars natural laboratories for testing Einstein's theory of general relativity under conditions that cannot be reproduced anywhere else, providing crucial insights into the fundamental nature of gravity, space, and time. During the violent core collapse that created the neutron star, one of the most dramatic demonstrations of conservation of angular momentum unfolds as the stellar core shrinks from a radius of thousands of kilometers to just 10 kilometers in less than a second. The original stellar core may have been rotating once every few weeks or months, but as it contracts by a factor of 100,000 in radius, its rotation rate must increase by the square of this factor to conserve angular momentum. According to the fundamental physics governing rotating bodies, this transformation converts a leisurely rotating stellar core into a cosmic spinning top that can complete hundreds of rotations per second. The newly born neutron star emerges from core collapse spinning faster than any other macroscopic object in the universe, with some achieving rotation periods measured in milliseconds rather than hours or days. If the neutron star's magnetic field is tilted with respect to its rotation axis, which occurs in most cases according to theoretical models of magnetic field generation during core collapse, the rapidly spinning neutron star becomes a pulsar, nature's most precise cosmic lighthouse. The misaligned magnetic field creates two beams of electromagnetic radiation that sweep across space as the neutron star rotates, much like the rotating beam from a terrestrial lighthouse sweeps across ships at sea. According to pulsar theory developed in the decades following their discovery by Jocelyn Bell Burnell in 1967, these beams originate from regions near the magnetic poles where charged particles are accelerated to tremendous energies by the rotating magnetic field. The lighthouse effect creates pulses of radio waves, X-rays, and sometimes gamma rays that arrive at Earth with clockwork regularity, allowing astronomers to measure the neutron star rotation period with extraordinary precision. The timing precision achieved by pulsar observations surpasses that of the best atomic clocks ever constructed by human technology. According to decades of pulsar timing data, the most stable pulsars keep time with an accuracy better than 1 part in 10 joule 15, meaning they would gain or lose less than 1 second over 30 million years of continuous observation. This incredible precision arises because the pulsar signal reflects the fundamental rotation of a massive object with a moment of inertia comparable to Earth's but compressed into a volume the size of a city. The neutron star's enormous density and small radius create a rotating system with such tremendous angular momentum that external forces can barely perturb its rotation rate. Millisecond pulsars, which have been spun up to extreme rotation rates through accretion from companion stars, achieve timing stabilities that rival or exceed atomic time standards, making them valuable tools for detecting gravitational waves and testing fundamental physics. The energy source powering a pulsar emission comes from the gradual loss of rotational energy as the neutron star's spinning magnetic field interacts with the surrounding electromagnetic environment. According to magnetospheric physics and observations of pulsar spin-down rates, the rotating magnetic field acts like a cosmic dynamo, accelerating charged particles and generating electromagnetic radiation at the expense of the neutron star's rotational kinetic energy. Over millions of years, this process gradually slows the pulsar's rotation from milliseconds to seconds, eventually causing the pulsar mechanism to shut off when the rotation becomes too slow to maintain the electromagnetic magnetic acceleration necessary for beam generation. The rate of energy loss follows well-understood physics of rotating magnetic dipoles, allowing astronomers to determine pulsar ages, magnetic field strengths, and internal properties from timing observations. Young pulsars lose energy rapidly and slow down noticeably over human timescales, while old pulsars have reached near equilibrium rotation rates and change imperceptibly over centuries. These natural cosmic timekeepers serve as fundamental tools for astrophysics, providing tests of general relativity through binary pulsar observations, enabling the detection of gravitational waves through pulsar timing arrays, and offering insights into the equation of state of nuclear matter through measurements of neutron star masses and radii. Not every massive star that undergoes core collapse will end its life as a neutron star spinning peacefully in the cosmos. For the most massive stellar cores, even the incredible resistance provided by the neutron degeneracy pressure and the repulsive strong nuclear force cannot halt at the relentless pull of gravity, and these stars face a darker fate entirely. According to theoretical calculations of neutron star structure and observations of neutron star masses in binary systems, there exists a critical mass limit beyond which no stable neutron star can exist, known as the Tolman-Oppenheimer-Volkoff limit, after the physicists who first calculated it in the 1930s. This limit lies somewhere between 2.5 and 3 solar masses, depending on the exact properties of nuclear matter at extreme densities. But once a neutron star exceeds this critical mass, not even the most exotic forms of matter can resist further gravitational collapse. When neutron degeneracy pressure finally fails, the core continues its inexorable collapse beyond nuclear density toward the ultimate gravitational abyss, a black hole. The transition from neutron star to black hole represents the most extreme transformation possible in the known universe, where matter disappears behind an event horizon and ordinary physics reaches its absolute limit. According to Einstein's general theory of relativity, the formation of an event horizon occurs when the gravitational field becomes so strong that the escape velocity equals the speed of light, creating a boundary in spacetime beyond which nothing, not even light itself, can escape to reach distant observers. For a stellar mass black hole, this event horizon forms at a radius of approximately 3 kilometers per solar mass, meaning that a 10 solar mass black hole would have an event horizon roughly 30 kilometers in diameter, not much larger than the neutron star that might have formed from a less massive core. The formation of stellar mass black holes through core collapse creates objects typically containing between 10 and 50 solar masses, significantly more massive than the neutron stars that result from successful supernova explosions. According to observations from gravitational wave detectors like LIGO and Virgo, stellar mass black holes in binary systems often have masses in the range of 20 to 30 solar masses, suggesting that the most massive stars either undergo direct collapse to black holes without producing visible supernovae or experience supernova explosions that are too weak to prevent significant fallback of material onto the central compact object. The process of black hole formation during stellar collapse may occur through several different mechanisms depending on the initial stellar mass and the success or failure of the explosion mechanism. According to three-dimensional simulations of stellar collapse, stars with initial masses above approximately 25 to 30 solar masses may experience failed explosions where the neutrino heating mechanism cannot revive the stalled shock wave, leading to continued accretion onto the proto-neutron star until it exceeds the maximum mass and collapses to a black hole within seconds of formation. Alternatively, even successful explosions from very massive stars may eject only a small fraction of the stellar mass, leaving behind iron cores massive enough to form black holes despite the supernova explosion. The most massive stars, those exceeding 150 to 200 solar masses, may undergo pair instability supernovae that completely disrupt the star, or they may collapse directly to black holes without any explosion at all if they lose their outer layers to stellar winds before reaching the end of their nuclear burning phases. Once formed, these stellar mass black holes represent regions where gravity has achieved absolute victory over all other forces in nature, creating space-time curvature so extreme that the very concepts of space and time break down at the central singularity. According to general relativity, the matter that formed the black hole continues to collapse toward a point of infinite density and zero volume, though quantum effects may modify this picture in ways that are not yet understood. The black hole's event horizon preserves information about the total mass, electric charge, and angular momentum of the collapsed star, but all other details about the original matter are lost to outside observers creating what physicists call the information paradox of black hole physics. Tonight, as we reach the final chapter of our cosmic story, we discover that stellar death represents not an ending, but the most profound act of creation the universe has ever devised. The massive star whose collapse we have followed from its iron heart to its explosive finale serves as a cosmic element factory, transforming simple hydrogen and helium from the Big Bang into the complex chemical inventory that makes planets, chemistry, and life itself possible. According to stellar nucleosynthesis calculations and spectroscopic observations of supernova ejecta, this single explosion disperses approximately 8 solar masses of oxygen into space, the element that will one day fill the atmospheres of countless worlds and flow through the bloodstreams of living creatures. The supernova also creates and distributes roughly 2 solar masses of silicon, the foundation for rocky planets and computer chips, 1 solar mass of iron that will form planetary cores and hemoglobin molecules, and half a solar mass of calcium that will become the bones and shells of future life forms. Beyond these abundant elements, the explosion performs an even more remarkable feat of cosmic alchemy through rapid neutron capture, or R-process nucleosynthesis, creating elements that cannot be forged by any other known mechanism in the universe. During the few seconds of core collapse and explosion, when neutron densities reach 10^24 particles per cubic centimeter, atomic nuclei undergo a cascade of neutron captures faster than radioactive decay can occur, building up the neutron-rich isotopes that subsequently decay into stable heavy elements. According to detailed nucleosynthesis models, this process creates approximately 10^4 solar masses of gold, enough to form all the gold jewelry that will ever exist on billions of Earth-like planets, along with platinum for catalysts, europium for red phosphors in computer screens, and uranium for nuclear energy and dating ancient rocks. The R process also produces gadolinium for medical imaging, terbium for green phosphors, and dozens of other rare earth elements essential for modern technology, making each supernova explosion a cosmic mint that creates the precious and technologically important elements scattered throughout the periodic table. The enrichment of the galaxy through supernova explosions follows a process called galactic chemical evolution, where each generation of massive stars lives, dies, and enriches the interstellar medium with heavier elements, gradually transforming the universe from its primordial composition of 75% hydrogen and 25% helium into the chemically diverse cosmos we observe today. According to computer models of galactic evolution, the first stars contained virtually no elements heavier than lithium, making them incapable of forming planets or supporting the chemistry necessary for life. But as these first-generation stars exploded as supernovae, they seeded the galaxy with oxygen, carbon, silicon, iron, and heavier elements, enabling the formation of second-generation stars with rocky planets and the potential for complex chemistry. This cosmic recycling program operates on timescales of billions of years, with each supernova explosion enriching a sphere of space hundreds of light-years in diameter with the products of stellar nucleosynthesis. The most profound realization emerging from our understanding of stellar evolution and explosive nucleosynthesis is that we are literally made of stardust, composed of elements that were forged in the nuclear furnaces of massive stars and dispersed by supernova explosions billions of years ago. The calcium in our bones was created during explosive silicon burning in a dying star. The iron in our blood was synthesized during the final moments of stellar collapse, and the gold in our jewelry was born during air-process nucleosynthesis in the most violent explosion the universe can produce. According to cosmic ray studies and meteorite analysis, even the trace elements essential for biological processes, from the zinc in our enzymes to the iodine in our thyroid glands, originated in stellar explosions that occurred long before our solar system formed. The supernova explosion that marked the end of our massive star's life becomes the beginning of a new cycle of cosmic creation, enriching the interstellar medium with heavy elements and triggering the formation of future generations of stars and planets. According to observations of supernova remnants and theoretical models of interstellar medium dynamics, the expanding shockwave from the explosion sweeps up and compresses nearby gas clouds over thousands of years, creating dense regions where gravitational collapse can initiate the birth of new stellar systems. The shock wave travels at several thousand kilometers per second through the tenuous interstellar gas, heating it to millions of degrees and creating a hot, bubble of X-ray emitting plasma that gradually cools and recombines over tens of thousands of years. As this supernova remnant expands and slows, it encounters giant molecular clouds containing hundreds of thousands of solar masses of gas and dust, compressing these clouds and triggering gravitational collapse in regions that might otherwise remain stable for millions of additional years. This process of triggered star formation creates a chain reaction where stellar death leads directly to stellar birth, ensuring that the galaxy maintains its population of massive stars despite their relatively short lifetimes of only millions of years. The heavy elements dispersed by the supernova mix thoroughly with the hydrogen and helium of the interstellar medium through turbulent motions and magnetic field interactions, creating a chemically enriched environment for the next generation of star formation. According to galactic chemical evolution models and observations of stellar abundances in different galactic regions, this mixing process operates efficiently enough to homogenize heavy element abundances across large regions of this galaxy within a few 100 million years. When new stars form from this enriched material, they inherit a chemical composition dramatically different from the first generation of stars that formed shortly after the Big Bang. These second and subsequent generation stars contain sufficient quantities of oxygen, silicon, carbon, and iron to form solid planetary materials during the star formation process. The presence of heavy elements in the collapsing gas cloud enables the formation of dust grains that can stick together and grow into larger solid bodies, eventually becoming asteroids, comets, and planets. According to models of planetary system formation and observations of exoplanets around metal-rich stars, the abundance of heavy elements in the protoplanetary disk directly correlates with the likelihood of forming terrestrial planets capable of supporting complex chemistry and potentially life. Rocky planets like Earth become possible only because previous generations of massive stars lived, died, and enriched the galactic environment with the silicon for rocks, the iron for planetary cores, the oxygen for atmospheres and water, and the carbon for organic molecules. This cosmic recycling program operates on galactic scales and billion-year timescales, gradually increasing the heavy element content of the universe from virtually zero after the Big Bang to the 2% heavy element abundance observed in our solar system today. Each supernova explosion contributes to this cosmic enrichment, adding its unique nucleosynthesis signature to the growing chemical complexity of the galaxy. The cycle continues as new massive stars form, evolve rapidly through their nuclear burning phases, and explode as supernovae, maintaining the production rate of heavy elements necessary to support ongoing planet formation throughout cosmic history. According to studies of galaxy evolution and star formation rates, this process ensures that roughly half of all Earth-like planets in the universe formed after our own solar system, inheriting even higher heavy element abundances that may enhance their potential for developing complex chemistry and biology. As we conclude our journey into the heart of stellar death, take a moment to consider the cosmic scale of these extraordinary events unfolding throughout the universe. According to observational surveys and theoretical estimates of stellar evolution, approximately one core collapse supernova occurs in a typical galaxy like our Milky Way every 50 years, a rate that seems almost leisurely until we consider the vastness of the observable universe containing hundreds of billions of galaxies. This means that somewhere in the cosmos, roughly 10 supernovae explode every second, each one representing the death of a massive star and the birth of a neutron star or black hole, each one dispersing heavy elements and triggering new cycles of star formation across cosmic distances. The observable universe witnesses approximately 300 million supernova explosions every year, making stellar collapse one of the most common yet most extreme events occurring in nature, a continuous background of cosmic violence and creation that shapes the chemical and physical evolution of galaxies throughout space and time. Future observations promise to revolutionize our understanding of these cosmic catastrophes through new technologies that can probe the collapse process in unprecedented detail. According to the rapidly advancing capabilities of gravitational wave observatories like LIGO, Virgo, and the planned Einstein telescope, we are entering an era where the gravitational waves produced by asymmetric core collapse and neutron star formation can be detected directly, providing real-time information about the dynamics of matter under the most extreme conditions imaginable. Advanced neutrino detectors like Hyperchamiocande, Juno, and Dune will be capable of detecting thousands of neutrinos from the next galactic supernova, compared to the 25 neutrinos detected from supernova 1987A, enabling detailed studies of the core collapse process, the neutron star formation mechanism, and the physics of matter at nuclear densities. These observations will provide direct tests of our theoretical understanding of stellar death and may reveal new physics operating under conditions that cannot be reproduced in any terrestrial laboratory. Despite decades of intensive theoretical and computational research, fundamental questions about the core collapse process remain unanswered, representing some of the most challenging problems in modern astrophysics. According to current three-dimensional simulations run on the world's most powerful supercomputers, the exact mechanism by which neutrino heating revives the stalled shockwave is still not fully understood, with successful explosions depending sensitively on the detailed three-dimensional dynamics of turbulent convection, the properties of the nuclear equation of state, and the complex interplay between neutrino transport and magneto-hydrodynamic instabilities. The question of which massive stars explode as supernovae and which collapse directly to black holes without visible explosions remains one of the most important unsolved problems in stellar evolution, with implications for understanding the population of stellar mass black holes, the chemical enrichment history of galaxies, and the formation of the most extreme objects in the universe. Each stellar collapse provides a natural laboratory for testing the fundamental laws of physics under conditions of extreme density, temperature, and magnetic field strength that approach the limits where classical physics gives way to quantum gravity and other speculative theories of matter and space-time. As we drift back from this cosmic drama to our quiet corner of the universe, we carry with us the profound realization that the elements in our bodies, the oxygen in our lungs, and the iron in our blood were forged in the nuclear furnaces and explosive deaths of massive stars that lived and died billions of years before our solar system formed, connecting us intimately to the most violent and creative processes the universe has ever devised. Tonight we have journeyed together through one of the most extraordinary stories the universe has to tell, following a massive star from its final breath through core collapse, neutrino storms, shock revival, and explosive death into the cosmic legacy that makes our very existence possible. We have witnessed physics pushed to its absolute limits, where quantum mechanics meets general relativity, where matter transforms into exotic states that exist nowhere else in nature, and where the death of one star becomes the seed for countless future worlds. The iron core that began our story as an Earth-sized sphere of stellar ash became a city-sized neutron star spinning hundreds of times per second, or perhaps collapsed beyond all resistance into a black hole where space-time itself surrenders to gravity's ultimate victory. We have seen how neutrinos, those ghostly particles that barely interact with ordinary matter, become the cosmic messengers that carry away the energy of stellar death and enable the explosive rebirth that enriches our galaxy with the heavy elements essential for planets, chemistry, and life. Every breath you take contains oxygen forged in the nuclear furnace of a dying star. Every beat of your heart moves iron through your bloodstream that was created during the violent collapse we have explored together. And the calcium in your bones carries the memory of explosive nucleosynthesis that occurred billions of years before our solar system formed. This is the profound truth revealed by modern astrophysics. We are not merely observers of the cosmic drama unfolding in distant galaxies, but intimate participants in a story of creation that connects us directly to the most extreme and beautiful processes the universe can produce. The stellar collapse that seemed like an ending reveals itself as a beginning. The death that appeared to be destruction becomes the ultimate act of creation, and the violence that looks catastrophic enables the cosmic recycling that makes complexity and consciousness possible throughout the cosmos. As you close your eyes tonight, remember that you are made of star stuff, forged in cosmic furnaces and scattered by explosions that outshine entire galaxies, carrying within your very atoms the legacy of stellar death and the promise of cosmic rebirth. If these quiet stories of cosmic wonder have brought you a moment of peace or sparked your curiosity about the universe we share, your gentle like, your soft subscribe, and your thoughts in the comments below mean more than you know. Share with us where you are listening tonight. What questions about stellar death still capture your imagination, and which part of this cosmic journey moved you most deeply? Your words, your presence, even your sharenets are like little stars in the vast constellation of minds that find beauty in the universe's most extreme physics. Until we meet again in the quiet spaces between stars, remember that each stellar collapse happening somewhere in the cosmos right now is writing the next chapter in the story that began with your very first breath.